Hi everyone, welcome back. Hope everyone had a very happy Canada Day. We are going to continue where we left off last time, and we're going to go over linear first-order ODEs and integrating factors again, since we were pretty rushed last time and didn't really have time to finish it up properly. So I'll be repeating some things today, since I figure some of you might have forgotten stuff in the last week, and so hopefully the review should go relatively quickly. So last week we discussed things like the existence uniqueness theorem. So if you're given a particular first order linear ODE and initial value an initial value problem, we know that there exists some unique solution. And in the more theoretical ordinary differential equations class, we spend a lot of time on existence and uniqueness theorems. But we're not going to do that in this class because, well, this isn't a very theoretical class. So just be assured that unless I tell you otherwise, every one of the problems I assign you will have a solution. Luckily, in practice, the fact that something works in real life often does mean that it has a solution. The other thing we covered last Wednesday was we covered what differentials are. So if you think about differentials as the sort of intuition behind, you can sort of think of them as infinitesimal changes along the x or y axes. And so this is sort of the intuition behind derivatives, because what you're doing is you're taking an infinitesimal change along the y-axis and then divided by infinitesimal change along the x-axis, and that gives you the instantaneous slope. These are also obviously very useful for things like integration, because you're basically using those to define the tiny rectangles that you're adding up together for the Riemann sums. One of the important things about these differentials is that you can think of taking the differential of a more complicated function, like df here, and in that case, you end up getting df is equal to x squared, and you can go backwards. So if you integrate df, that is equal to the integral of x squared dx, and so then f is equal to 1/3 x cubed plus c, which recovers the original function. So taking a differential of a function is basically equivalent in some sense to taking a derivative, except you've split apart the two different parts of the derivative. We also talked about more complicated differentials, so these were of multivariable functions. Oh, wait, so sorry, my animation still needs to go. So these were for multivariable functions, and you can think of the differential as basically combining together the information of how your function z, or f, changes as you go infinitesimally in the x direction and infinitesimally in the y direction. And we gave a couple examples of this, where we took a particular function, z, or f, of x and y, and then we took the differential by what we did is dz is equal to the partial derivative with respect to x times dx plus the partial derivative with respect to y times dy. Okay, any questions on that so far? So this is all a review from last time. And then last time I also had you guys compute a couple of these, and you guys seem to be fine at doing that. So now this is the process of computing a total differential. Now there's the question of how do you, and so this is where new material starts today. How do you reverse a total differential? Well, suppose that we have dz is equal to 2x plus 2y times dx plus the quantity 2x plus 4y squared times dy. So now what we have to do is we have to solve for the partial derivative of z with respect to x is equal to 2x plus 2y, and the partial derivative of z with respect to y is 2x plus 4y cubed. So let's do those step by step. Let's first solve for this one. Well, if we take the integral, well, what we get is that we get z is equal to the integral of 2x plus 2y dx, and note that y here is a constant. So as far as this integral is concerned, y is a constant, and so z is equal to x squared plus 2xy plus some constant. But remember that y is a constant, so we can have some function of y. So this is where we normally have c. Instead, we have some arbitrary function of y because y is a constant. On the other hand, we have this other integral that z also needs to satisfy. So z is also equal to the integral of 2x plus 4y cubed dy, where x is treated as a constant. So z is also equal to 2xy plus y to the fourth, but x here is a constant, and so there's some other function g of x. So now when we're actually computing for z, we need to combine these things together. So we have z is equal to, well, we have this x squared here, so it obviously needs to have an x squared. We have this 2xy here, which appears in both. And then we have, let's see, this f of y, which corresponds to this y squared, plus y squared, sorry, y to the fourth. And we also have this g of x, which doesn't correspond to anything here, but you can think of it as corresponding to plus 0 here. Okay? And so this ends up, or you can, giving you z is equal to x squared plus 2xy plus y to the fourth. And you can think of this as plus c, because of course you can add a constant when you're doing these sorts of things and it doesn't change anything. And if you take the total differential of this function, you'll find that this does give you dz back. Why does f of y correspond to y to the fourth? Because f of y is a function, so over on the red integral on the left, since I'm mirrored, in the z integral, what we know is that it's x squared plus 2xy plus some constant. But because here on this side, sorry, let me do for this here, y is a constant, and here x is a constant, which means that the constants can include y. So this constant can't, and so this is why we have this f of y and why we have this g of x. Oh, yes, sorry, yeah, that is correct. The g of x actually does correspond to the x squared. Thank you for, I wrote that wrong. Yep. Yeah, so g of x corresponds to the x squared, the 2xy is the same, and the f of y corresponds to y to the fourth. Sorry if that was confusing. Yeah. But basically, you have two different integrals that z needs to satisfy, and then you match together the different parts, and that gives you a guess for what z could be. And one of the things you can do is you can then check that the dz actually is the total differential we had written out above. Okay? So, you can go forward, you can go backwards, and it's a little bit complicated because you have to take integrals twice, and then you have to match them together, but you still can reverse the total differential this way. So let's have you all try it out. So try it out. Find z such that dz is equal to this complicated thing, 2xy times e to the x squared y times dx plus x squared times e to the x squared y plus 5 times dy. And these are your possibilities. And let me reset the poll before we get started. So remember, you have to do here is you have to set z equal to two different things. So z is equal to the integral of 2xy e to the x squared y dx, and z is equal to the integral x squared e to the x squared y plus 5 dy. Okay, so I'll give you a moment to figure this out. And remember that when you're taking these integrals, on the left one, you should treat y as constant, and on the right one, you should treat x as constant. Because you're basically reversing the partial derivatives that you would have taken to on z in order to get that, the different components. Okay, looks like we have our first answer. So it looks like, and let's wait another moment or two to let other people finish up. Okay, it looks like we do have consensus around A. Okay, yeah, and when we write this out, what we get on this left-hand one is we get e to the x squared y. And of course, you need to do a u substitution here, but I'm just going to do it implicitly. So z is equal to x squared y plus some function of y, because of course y is constant there. And z is equal to e to the x squared y plus 5y plus some function of x. And you get that z is equal to e to the x squared y plus 5y. Plus c, but we are going to mostly ignore those for the time being. Okay, and so that is actually A. Okay, so now we know how to reverse things. What happens when does it always work? Well, unfortunately, the answer is that sometimes reversing fails. So, for example, in this particular one here, I have z is equal to the integral of y squared dx, and z is equal to the integral of x squared dy, and you end up with z is equal to xy squared plus some function of y, and z is equal to x squared y plus some function of x, and these cannot be set equal to each other. Unfortunately, this doesn't work. And when this happens, we're going to call it something called not exact. And this is a definition that we ended with last time, but I didn't really have time to go into it. Basically, if you can't reverse it, if it isn't the total differential of some function, then the dz is not exact. Let me repeat that with the slide I had last time. So let's see, where was I? So when we talked about exact differentials last time, basically a differential, dz is equal to some p of xy dx plus q of xy dy. This is an exact differential if there exists a function f of xy such that p of xy is the partial derivative of f with respect to x, and q of xy is the partial derivative of f with respect to y. In that particular case, then z is equal to f of xy. In other words, an exact differential is any differential that is the total differential of some function. So often you'll hear people use the words exact and total used in interchangeable ways, and they're basically interchangeable. There are slight differences. Usually, you talk about differential being total differential only when you're focusing on the function that it's the total differential of. Whereas an exact differential is just any differential expression that is the total differential of some function. And an inexact differential is a differential expression that we write down that is not the total differential of any function. So in this particular case here, this is not an exact differential because you can't reverse it. So now, one way to test for exactness is to try to... Oh, I forgot to put in my animations for this. That's all right. One way to test for exactness is to try to reverse the differential. This will always work, but it will involve a lot of integration. Happens to be a faster test that involves only differentiation. So recall that for most nice functions, we have that the partial derivative in the second order partial derivative d squared del squared f del y del x is equal to del squared f del x del y. So if you flip the order of the partial derivatives, for most nice functions, those are equal. And it turns out that a quick way to see if a differential dz is equal to p of xy dx plus q of xy dx dy, the quick way to check to see if that's exact is to take the partial derivatives dp del p del y and del q del x. And the reason this works is because this thing here is del y of del f del x, and this thing here is del x of del f del y. Okay, so this is just another quicker way of figuring out whether or not a differential is exact. Let's see. I did a couple examples last time. I'm going to do them again, so I'll be repeating myself a little bit, but hopefully this time they'll make a little bit more sense. So the whole point is that you can always just use integration to try to figure out whether or not the differential is exact, but the quicker way is to take these additional partial derivatives. So for example, and I'm just going to use the examples from last time, if del z is equal to 10x over y minus 1 dx minus 5x squared over y minus 1 squared dy, here we have this thing here is p of xy, and this thing here, including the negative sign, is q of xy. Then del p del y is going to be equal to minus 10x over y minus 1 squared, and del q del y is also equal to minus 10x over y minus 1 squared. And so therefore, this one is exact. And if you wanted to, you could use integration to figure out what this is the total differential of. But we're not going to bother doing that. You can also, let me give an example again where it fails. If you have 5x squared plus 1 dx plus x squared y, xy squared. Let me give the right example. Xy squared dy. So here, this is p of xy, and this is q of xy. Del p del y is equal to 0, because x is a constant as far as del y is concerned. Del q del x is equal to y squared. So this here is not exact. Okay? So this is just a faster way of figuring out if things are exact or not. If you are unsure about how to apply this test, you can always just try to take the integral. But that's oftentimes more time consuming. So let's try it out. Let me reset my poll here. Let's go to trying it out. So, are these exact, inexact, both exact and inexact, question mark, or none of the above? Let's start with this one. dz is equal to x dx plus y dy. Okay, so it looks like we have a lot of replies, and it seems like everyone seems to agree that this is A, so this is exact. Well, let's take a quick look. So we have del y of x, that's equal to 0. We also have del x of y, which is also equal to 0, and so this turns out to be exact. In fact, I can go ahead and give you an example. If z is equal to 1/2 x squared plus 1/2 y squared, then you'll get that answer. Now, you can compute that you can compute the actual value for z by doing the integration, but here we're just testing for exactness. Okay, let's try this one. What if I swap the x's and the y's? Let me reset before you do anything. Okay, so what are we getting? We're getting a number of b's. Let's see, we did get one A, so let's see how many people have voted. Well, let's take a look at this. So what are we asking? We're asking del y of y. Well, what's that? Well, that's just equal to 1, right? And we have del x of x, which is also equal to 1. So these are actually equal, and so this actually is exact. In fact, the one solution to this is z is equal to xy. If you take the total differential of xy, you will actually get dz is equal to y dx plus x dy. And so this is actually exact after you take the partial derivatives. So it looked like most people got that wrong, so hopefully you understand why you got that wrong, and let's try again. So let's try the next one. Let me reset before you start replying. So if we have x dx plus y squared dy, is this exact? So note that don't get confused about exact and separable. Those are two completely different concepts. I know we talked about separable last time. That is a completely different concept. And for this concept, you do have to take these derivatives. Okay, so it looks like we got a number of replies. Okay, so people think this is exact. Well, let's work it out. So we have del y of x, which is equal to 0, and del x of y squared, but y squared is constant as far as del x is concerned, and so this is also equal to 0, and so therefore this is actually exact. And this one solution happens to be z is equal to 1/2 x squared plus 1/3 y cubed. In fact, in this particular case, it should be fairly easy to see that it's exact, because what you could have done is you could have just plopped in integration signs, and you get the same answer. So if you had plopped in integration signs here and here, that's actually the answer you would have gotten, and that would have been correct. Oh, I just erased way too much. Sorry, let me fix that. Okay, so how do you find the solution again? We'll go through finding the solution again in a moment. I don't have enough space on the slide to do it, so we will go through another example of that in a moment. Okay, so now let's try swapping the y squared and the x. So is this exact? And let me reset before anyone replies. Okay, so it looks like the responses are trickling in, and people seem to think that it is inexact. Well, let's try it out and see what happens. So del y of y squared, well, that is equal to 2y. And del x of x, that's equal to 1. And these are not equal. So therefore, this is inexact. Okay, and look, seems like most people got that right. Let's go on to the last one, and let me reset before you guys do anything. So x plus y dx plus x plus x plus y dx plus x plus y dy. So is this exact or not? Okay, looks like most people agree on A, though we have a few B's in there. Well, let's try it out. So, del y of x plus y. Well, as far as del y is concerned, x is a constant, so this is just equal to 1. And del x of x plus y, that's also equal to 1, and so therefore this is exact. One solution to this happens to be z is equal to x plus y, 1/2 x plus y squared. Okay, so now that we have all this, this machinery, we can solve exact differential equations. So if you have a differential equation, so let's suppose that, let me write this out. Let's suppose that we have a differential equation. I'm going to use dy dx notation because we're going to be separating the differentials in a moment. It's equal to minus 2xy over x squared plus 1. Okay, so now if we have this equation, well, what do we want to do? Let's first try to write things out. So you end up getting that multiplied out, x squared plus 1 dy is equal to minus 2xy dx. And if we rearrange this, actually one thing you should notice is that for this particular problem, you actually might be able to separate it. And so this problem is separable, and so you can use the separable techniques to solve this, but we're going to solve it a completely different way. We're going to solve it by using the fact that it is an exact differential equation. So let's rearrange this. We end up getting 2xy dx plus x squared plus 1 dy is equal to 0. And notice that this is a differential expression, and you have del y of 2xy is equal to 2x, and you have del x of x squared plus 1 is equal to 2x. So this is exact. And so this is exact. So now let's try to let's try to compute what the differential is the differential of. And so we need to take the integral of 2xy dx, and that's equal to, so this integral with respect to x, this is equal to x squared y, and plus some function of plus a constant, which could be a function of y. And we do the other one, the integral of x squared plus 1 dy. So note that this is this one here, and this is this one here. This is equal to, well, again, you get an x squared y plus some function of x. And when you combine these together, you end up getting that a test f of x y is equal to x squared y plus y as a function f that for which this is the total differential. But now note that, of course, we also know that df is equal to 2xy dx plus x squared plus 1 dy. And this entire thing corresponds to this entire thing. And so therefore, we know that df is equal to 0, right? And we can take the integral. So then the integral of df is going to be just f plus c. So you're reversing the integral here. And that implies that x squared plus y, x squared y plus c is equal to 0. And then that implies that we have x squared plus 1 y is equal to some other c. So we're I'm playing fast and loose with my constants here. This is actually minus c. Oh, sorry, I have an extra parentheses there. Which implies that y is equal to c over x squared plus 1. And you can double check by plugging this back into the original differential equation, and you'll find that this is actually a solution. Could you explain below the red line? Ah, yes. So this is the tricky part, right? So we have this red line here where we said that 2xy dx plus this thing is equal to df, right? And we have another equation over here where this entire thing is equal to 0. So that's equal to 0, right? So that's equal to 0 now, and so therefore df is equal to 0. And now we're taking the integral, and so when you take the integral of df, we know that the integral of df is equal to f plus c. But we also know that this is equal to the integral of 0. And if you take the integral of 0, that just happens to be equal to 0. And so therefore you're left with f plus c, so this entire thing is f plus c is equal to 0. And after that, it's just a matter of manipulating it algebraically. Okay, so hopefully that made sense. This is going to be one of the more difficult concepts that we're discussing. Why is it equal to f? So remember that if we have the integral of dx, that's equal to x plus c, right? The integral of dy is equal to y plus c, etc. And so the integral of df is equal to f plus c. Okay. So, like I said, this is somewhat complicated. The basic idea is that if you can take the derivative of anything, you can always reverse it. And so, oh, what just happened to my... Oh, no, it came back. Okay. Yeah, so if you... why is it x squared y plus y? Okay. So, now remember, we also had this up here. So here, this is f is equal to x squared y plus y. So remember, the x and the y of f of x, y are just saying that f is a function of x and y. So now we're using f as a variable itself. And so then you plug in x squared y plus y in for f. Okay. So now the whole point of this was that whenever you take a derivative of a function, well, you can always reverse it. When you integrate the entire the derivative, well, that gives you back the original function. So this is back to the basically the fundamental theorem of calculus. So now this is a slightly more complicated form of it, where you're taking these multivariable derivatives and integrations. But now, this is super important because it means that if your differential equation has this form to begin with, you can solve it in this way. So this is another tool that we have for solving exact differential equations. Okay, so moving on to the next slide. That only works if we have an exact differential equation, right? So if our differential equation was inexact, then that wouldn't work. But sometimes you can find an integrating factor. So some magical function you're going to multiply both sides by to turn an inexact ODE into an exact ODE. So let me give an example of that. So let's suppose that we started with some differential equation, xy prime plus 2y is equal to 5x cubed. Well, if you rewrite this, this is x times dx dy dx plus 2y is equal to 5x cubed. If you multiply everything by dx, you end up with, and then rearrange, let me do it in steps. So x times dy plus 2y dx is equal to 5x cubed dx. And if we rearrange that, we get 2y dx plus x dy is equal to 5x cubed dx. So now what we want to do is we want this left-hand side to be exact. So ideally this would be exact. Well, is it exact? Well, let's test it out. So del y of 2y is equal to 2, but del x of x is equal to 1. So this is, and these are not equal, so this is not exact. But now let me just introduce a magical function. Let I of x be equal to x, and what we're going to do is we're going to multiply everything, multiply by I of x on both sides. And so then what happens is you end up with, if you go from here to here, you end up getting 2xy dx plus x squared dy is equal to 5x to the fourth dx. Okay, did everyone understand that step? I just took the entire thing and multiplied everything by x. Now, this is a little bit weird, of course, because this is, let me go through it again slowly, because this is a little bit weird, everything I did. So the first couple things we did is we just rewrote, right? So we rewrote from here to here, all we did was we rewrote y prime as dy dx, which it is by definition. The next thing we did is we just rearranged everything around by multiplying by dx and then doing some algebra, right? So going from here to here, we multiplied by dx, right? And here to here, that was just a rearrangement. And then what we would have hoped is we would hope that it is exact. But unfortunately, it's not exact. And so things don't work out so nicely. So instead, what we're going to do is we're going to do this weird operation. We're going to multiply this equation by x on both sides. So remember, when you have an equation, so if you have an equation x is equal to 5, you can multiply it on both sides by, and you know that 2x is equal to 10, and that's still true. Or x squared is equal to 5x. Those are all still true statements if you multiply on both sides. And so here, what we've done is we multiplied on both sides by x. And we have this new differential expression that is equivalent, well, mostly equivalent, to the original one. But now there's something really, really cool about this new differential expression, which is that it is actually exact. So dy of 2xy is equal to 2x, and del x of x squared is equal to 2x. So this is now exact. And using the techniques we discussed in the previous couple of slides, you can let f of x y is equal to x squared y, and x squared y will actually be the function for which that is the total differential. And then what you get is you end up with df is equal to 5x to the fourth dx. Okay? And then you integrate on both sides. And that results in f is equal to x to the fifth plus c, which gives you, what was f? F was x squared y, so x squared y is equal to x to the fifth plus c. and that gives you the solution. How do we know that f is equal to x squared y? You have to use the techniques that we used. Wait, sorry. So you have to use the techniques we used here, where we took both integrals. So I just skipped that step because otherwise going through every single one of the steps would take up too much space on the slide. But yeah, so you would have to actually do that step. We're just skipping that step here because that's not what I'm trying to introduce here. So once you've done that step, you'll find that f of xy is equal to x squared y, and then you can do this process. Okay, so let's have you all try it out. So I'm going to give you an inexact differential equation. Let me reset my chat. And I'm going to ask you which of the following is an integrating factor. So I'm not going to ask you to solve the entire thing. I'm just going to ask you which of these possible things is an integrating factor. In other words, if I multiply both sides of this equation by each of a, b, or c, do you get an exact differential equation? And I'll give you all a moment to work through this. Okay, so it looks like we have a critical mass for A. So let's try out all three of them, just so that we get practice. So, in the very first one, we multiply everything by x. So we have 2x dx is equal to 1 over x dx plus 1 over y dy. And then del y of 1 over x is equal to 0. And that also happens to be equal to del x of 1 over y. So yes, this is exact. On the other hand, if we try x squared, you end up getting 2x squared dx is equal to dx plus x over y dy. And then you get del y of 1 is equal to 0. But you have del x of x over y is equal to 1 over y, and so this is not equal. And lastly, so this is not exact. And lastly, we have, if you multiply by xy, you get 2xy dx is equal to y over x dx plus dy, and del y of y over x is equal to 1 over x, and del x of 1 is equal to 0, and these are not equal, so not exact. And so our solution, I'm going to do this in red, is just A. Okay, and once you convert it into an exact equation, then all you have to do is then you need to find the function that it's the total differential of, and then you integrate both sides. So now, those of you who've been following along in the book have probably noticed that we've gone into much more detail on this than your book does. And part of this is because this is a more advanced technique that I want to introduce because I'm trying to explain how we have a formula that I'll be introducing later for linear first-order equations. But there are a couple caveats to this method that we just introduced. So, there's a very important fact. Every first-order ODE can be turned into an exact differential using an integrating factor. So in theory, if you could guess the right integrating factor, you could solve any first-order ODE. Unfortunately, there's another fact, which is that there's no systematic way of guessing integrating factors in general for general ODEs. We just don't know how to do it. Like it doesn't. There are ODEs for which first order just means only a first derivative, not to the power. So here, in this case, we're talking about the order of an ODE, which is talking about how many derivatives, not the order of a polynomial, which is how many powers. But yeah, so in terms of integrating factors, there's no systematic way of guessing. Therefore, in this class, in MATA35, we will not expect you to use integrating factors outside of a few special cases where the integrating factors are known or where we will give you a hint. So don't worry, I'm not going to give you an arbitrary inexact ODE and ask you to solve it. If I give you an ODE and tell you to solve it using integrating factors, it'll be because it's of a particular form for which we know how to do, for which we know an integrating factor already. Okay, now, what particular forms do we care about? So if you go all the way back to the beginning of lecture, one of the things we cared, if we go all the way back to last lecture, one of the reasons we went on this big winding path is because we wanted to find we wanted to solve a linear first order ODE, which has this following form: y prime plus p of x y is equal to q of x. You can rewrite this as dy plus dx times p of x y is equal to q of x by just multiplying everything by dx. Sorry, there should be a dx here. And then once you've done that, the integrating factor, we know this integrating factor, it's e to the indefinite integral of p of x dx. This is just something we know, and it's something that you should keep in mind and remember, because this is just a well-known fact. Let me give an example to hopefully make it a little bit more clear. And so let's suppose we had xy prime plus 2y is equal to 5x cubed. So the first thing you'll notice is that this isn't in quite the right form. And so the first thing we're going to do is we're going to divide everything by x to put this in the right form, which is y prime plus some p of x. So this p of x is going to be 2 over x. Y is equal to 5x squared. So we divided out x from everything. And then remember that y prime is just dy over dx. And so we're going to multiply everything by dx. And so you get dy plus 2 over x times y dx is equal to 5x squared dx. I'm going to rearrange this to put it into a nicer form. So this is 2 dx times 2y over x plus dy is equal to 5x squared dx. And we know our integrating factor is equal to e to the integral of 2 over x dx. That's just an assumption, which you should memorize. And this is equal to 2 to the e to the 2 natural log of absolute value of x, which is equal to e to the ln of x squared, which is equal to x squared. So our integrating factor here is equal to x squared. So now note that we have to put it in this canonical form first. So we're going to take this and we're going to multiply by I of x. And so then that's going to leave us with, oh, sorry, that's not quite the right form. Take this bottom one. So, and we're going to multiply by I of x. So we're going to multiply by I of x, and then we're going to end up with dx times 2xy plus dy times x squared is equal to 5x to the 4th dx. Okay, and it turns out, I'm not going to test it here, but it turns out, and you guys know how to do this now, this thing here is exact. And what you'll end up with is, if you are trying to solve this equation, you'll end up with skipping a couple of steps. So I'm going to skip a couple of steps. This is going to give you x squared y is equal to x to the 5th plus c. Okay, so I skipped multiple steps there. Let's see, hopefully I did that right. X squared y, yeah, yep, is equal to x to the 5th plus c. Now let's go back and just go over it again to make sure everyone knows what we're doing. So the first thing we did is we just rewrote. So this step, we divided by 1 over x. This step, we multiplied by dx. This step, we just rearranged. Okay, because what we want to do is we want to put it in the exact same form. So we want this in the form where we have a dy and we have a dx and we have a p of x. P of x times the p of x here is just 2 over x. So let's actually let me rewrite this in a slightly different form so that it makes it more obvious. So this is 2 over x times y. So we have our p of x and we have our y. And we take our p of x and we put it up here because that's what we know because that's where our p of x goes. Okay, does anyone have any questions about that? So this is how you solve a first order ODE. It turns out that we know what the integrating factor is, and it'll end up in a fairly nice form because sorry about that, I had to cough. But yeah, so you'll end up with this nice form. You use that integrating factor, and you can solve any linear first order ODE by rewriting and using this algorithm. Let's go through all these steps of the algorithm again, just to make sure. So if you rewrite a linear first order ODE in this form, y prime plus p of x y is equal to q of x, and you can rewrite every linear first order ODE in this form, then you can find the general solution by first determining the integrating factor, which is just I of x is equal to e to the integral of p of x dx. You multiply both sides by I of x. You multiply both sides by dx. And then the left-hand side is the total differential d of I of x y. So this is just something that happens to be true. And this will always be true for linear first-order ODE. And so then you can integrate both sides to get I of x times y is equal to the integral of q of x I of x dx, which is an integral in one variable, and we know how to do that. And so therefore y is equal to 1 over I of x times the integral of q of x times I of x dx plus c. And if you wanted to, you could write it in a single big, long, ugly equation, which I'm not going to bother reading out since it's just what all the other steps did. So if you wanted to, you could just memorize this equation, and so long as you put the linear first-order ODE in that form, you can just plug everything in, and I'll give you the answer. I find it much easier to go through all the steps because those steps are general instead of memorizing this equation. Okay, and for the last part of this, the first half of today's lecture, I'm going to have you all try it out. So we have y prime minus 3x squared y is equal to x squared. I have already put this in a canonical form, almost a canonical form, and so hopefully you'll be able to answer what is the integral, what is y equal to? And let me reset the chat for... So let me go ahead and give a quick hint, which is that p of x is equal to minus 3x squared, and q of x in the previous example is equal to x squared. So of course, the first thing you need to do is you need to figure out this integrating factor. But there's a formula for that on the previous slide. Oh, yeah, let me flip back for a bit to let you guys see the various formulas. So these are all the steps you need to take. So the first thing you do is you solve for the integrating factor. I of x is equal to e to the integral of p of x dx. Then you multiply both sides by I of x, you multiply both sides by dx, and then you know what the left-hand side integral is. So you can, if you want, you can take the time to figure out what the function f is. Or it turns out that for this particular type of equation, that function will always be I of x times y. And then you can integrate both sides, and that gives you the equation. Okay, let me go ahead and give you the integrating factors, since hopefully you guys have... Yep. So let me go forward again, and let me go through the integrating factor, which is going to be equal to e to the integral of p of x, so minus 3x squared dx. And so this is equal to e to the minus x cubed. It turns out, for reasons that I don't really want to explain, though you can sort of work out yourself, that you don't need to worry about the constants for this indefinite integral. If you leave it in there, you won't get the wrong answer, but you don't need to worry about it. Yeah. So once you have this step, then all you have to do is you just multiply everything. So if you were to rewrite it, you could rewrite it as minus 3x squared y plus dy dx is equal to x squared. Multiply everything by e to the minus x cubed. So minus 3x squared e to the minus x cubed times y dx plus e to the minus x cubed dy is equal to x squared e to the minus x cubed dx. Okay, it looks like we're starting to get, we had one guess of B, though, with a question mark. So let me go through and do a couple more steps. And let's see what happens. So there are a couple of steps we need to do. So what we're going to do is we're going to take the integral of everything, right? So we're going to take the integral of this, and we're going to take the integral of this. But now, notice that we know what this integral is. That integral is just I of x times y. And we know this to be true. You can prove it if you want, but it's pretty straightforward. So therefore, this thing here is equal to y e to the minus x cubed. And then you need to take the integral of this thing. So what is the integral of this thing? Well, the integral of x squared e to the minus x cubed dx. Well, we do a u substitution. U is equal to x cubed. Du is going to be equal to 3x squared dx. So this entire thing is equal to 1/3 integral e to the minus u du. And therefore, this is equal to minus 1/3 e to the minus u plus c. And so this is equal to minus 1/3 e to the minus x cubed plus c. But now here is the place where you guys have to be a little bit careful. So, although I wasn't entirely clear about, so this thing here is equal to minus 1/3 e to the minus x cubed plus c. But now we have to, if you want to solve for y, we actually need to get y is equal to minus 1/3 plus c times e to the x cubed. And so the answer is actually D. And the thing that I think most people forgot to do is you forgot to multiply both sides by e to the x cubed in order to actually solve for x, or solve for y. Okay. I think. Oh wait. There. Sorry. So remember, when you after you do that step, you have y times I of x, and so if you want to get the actual answer, you then need to divide by I of x as well. So remember, if you go back to the formula, you end up with you have to divide by 1 over, you have to multiply by 1 over I of x, or divide by 1 over I of x, or divide by I of x in order to get the actual answer for y. Okay, so I am going to stop there for this half of lecture. Let's take a, say, 9-minute break and come back at 1:15. And I'm going to stop recording, and in the second half of class, we're going to be talking about autonomous equations. I will see you then.